Okay, hello everybody. Welcome back to another lecture of artificial intelligence. So where did we stop yesterday? Yesterday we talked about Bayesian networks, and Bayesian networks are very useful to store all the information that you need to compute the joint probabilities or any kind of probabilities of random variables. And of course, the larger the network becomes, the more computationally intensive is the computation of the probabilities. And one possibility that we have is to approximate probabilities using Monte Carlo simulation. And as I mentioned already yesterday, so when you use logics, you cannot just approximate logics because you just want to know whether it's true or false. But when you compute with probabilities and you want to know what is the probability, for instance, that I don't know, you have a great party tomorrow, despite being in a Corona situation. Of course, now it's very low, but if you want the exact probability would be maybe 10%. And if you approximate it by 8% using a faster method, then this in many applications is good enough. So some of you might already know how Monte Carlo simulation works. And for those that don't, it's actually a very simple procedure. So you just create samples, because creating samples from a given probability distribution is computationally cheap and easy to implement. Then you perform some deterministic simulation. Also, simulating a problem is often much easier than computing the new probability distribution. And in the end, you just have a lot of samples that have been forwarded or propagated over time or propagated through some dynamics. And then you aggregate all the results and then count the number of cases for which a certain event is true or false, and then you obtain a probability. So there exist mainly two directions: direct sampling methods, which is used on the next slides, and also more complicated methods like Markov chain Monte Carlo methods, which are presented in the AI book in section 5.2, but we are excluding this from here because as most of you, I mean, we have enough content for this lecture, as most people would agree. By the way, we have initiated a request that the lecture in the next years will be 3+2 instead of 3+1, so that we have more time for the exercises. But this will take a long time because our lecture is mandatory in 2 study programs. Just so that you know that we're working on slowing down the lecture a little bit in the future and having more time for the exercises. Before I continue, I can just give you a very simple example of how you could use Monte Carlo simulation so that you get a feeling what Monte Carlo simulation means. So for instance, you can use Monte Carlo simulation to obtain the value of pi. So how do you do that? You just have a square, and you have a circle inside the square of radius r. And of course, the area of the circle is p times r squared. And the radius of the square would be, so the area of the square, so a square, is 4 times r squared, because the length is 2 times r of one edge. And if you square this, then you have 4 times r squared. So now when you sample the system, and maybe I change the color, then you would randomly create dots or samples inside the square. And then you count the number of dots inside the circle and inside the circle compared to the total number of samples that you have. So basically, you want to have the ratio of the number of points inside the circle and the number of total points. And of course, if you sample uniformly, this will be proportional to the areas. And then what we have is that r square cancels out. And now if we bring the 4 to the other side, we have that p equals n over n total multiplied with 4. This is not the most efficient way of computing the number or approximating the number pi. there was also recently a record in I've seen it in the news that the number of pi has been now computed for a huge number of digits. I forgot which number, but they use then different procedure. It just should showcase how Monte Carlo simulation in principle works, because everybody is familiar with the number pi. So yeah. Okay. So let's continue with the lecture. So let's continue with an example that is more relevant in the future when we have more severe climate change. So let's say you have a house, and of course in the future, because it's not very climate friendly, you shouldn't have your own house. You should maybe live in a like a house where several families are living in. And nevertheless, I'm not going to start any political discussion right now, but you have a lawn, and then this should be automatically watered. And so if you have a cloudy situation and you have a sensor for that, then this depends on whether the sprinkler is switched on or off. So if it's cloudy, of course, you shouldn't wet the grass. And if it's not cloudy, you should switch the sprinkler on. And of course, if it's cloudy, the chance of rain is high. And whether it's real rain or whether you have artificially watered your grass, in the end, your grass is wet. Okay, so there could be still some cases, let's say, if the sprinkler is on and it is raining, this model says, okay, it's only with 99% true that the grass is wet in the end. Maybe this could be a situation where your ground is so dry that it takes some time to wet it, and it's not sufficient just with one time of rain. Yeah, it's not, you could also use maybe 100% here if you want, depending on the situation. Okay, so now if you want to know maybe certain probability, for instance, what's the probability that the grass is wet, then what you can do is that you can just start creating samples, as I've shown to you, using this pi example. So initially, the probability that it's cloudy is 50%. And in this case, the sample is true. So we say, yes, it's cloudy. It could have been false. So if you sample this 100 times, it should roughly be in 50% of the cases cloudy and in 50% not cloudy. And of course, if the number of samples goes to infinity, then half of the samples would be cloudy and half of the samples would be not cloudy. Then based on this information, we can determine the probability that the sprinkler will switch on. So if it's cloudy is true, then the probability that the sprinkler is switched on is 10%. And the probability that it will rain is 80%. So now let's sample first the sprinkler. So this is false. This is the more likely event. And for rain, we sample that it's true, so which is also the more likely event. Now we know the sprinkler is off and rain is it's raining. And so sprinkler false is here and rain true is here. So then we have a 90% chance down here that we will have wet grass. And then we sample and we have wet grass. And this way we create many, many samples. So essentially what we have is that we have in the end a probability of the joint sample. So in our case, it would be cloudy, not sprinkler is off, it's raining and it's wet. And this joint probability of this sample can be computed by multiplying the probabilities of the individual samples. And the individual samples have been created by the conditional probability of xi given the parents of xi, because we have a Bayesian network. And if you remember, by using this formula, we know that this returns the joint probability of the of our random variables. Okay, so then the probability of creating a sample equals also the probability of this joint event. So for instance, for our sprinkler case, now we insert the numbers 0.5, 0.9, 0.8, 0.9 again, and then we obtain this number, and this is then equals the probability of this joint event. Okay, so now this is not how Monte Carlo works. It's just like an intermediate result that we need later on. Monte Carlo, of course, works by counting the number of cases. So let's denote with NPS the number of samples generated for this specific event, joint event from denoted by x1 to xn, and p hat returns the estimated probability. And if the number of samples goes to infinity, then this estimated probability will be the number of samples for which this joint event is true divided by the number of total samples, which is the first line here. And of course, if the number of samples goes to infinity, this will equal the probability of these samples. And by using here this formula, maybe I just use the pen again. So we are inserting, sorry, I have to change something here. So we are inserting this equality here. Then we obtain that if the number of samples goes to infinity, that the probabilities we obtain by counting the number of samples for which the joint event is true divided by the total number of samples, then we approach the true probability distribution. And because that's the case, we say that the estimates are consistent so that the estimated probabilities approach the true probabilities if the number of samples goes to infinity. Of course, if the number of samples actually goes to infinity, this would take more time to compute than using our previous example. So we will use much less samples and hope that the probability is good enough. So it just should show that the more samples you have, the better is the result in the end. So this is, computing joint distributions is simple, but what we often want are conditional distributions. And for that, we will look at two methods. The first one is rejection sampling, which is the easier method, and the other one is likelihood weighing. So let's start with the easy one. So we use this to obtain a hard-to-sample distribution given an easy-to-sample distribution. So easy-to-sample here is the joint distribution, and hard-to-sample is then this conditional distribution. So we consider the simple form of determining the conditional probabilities P of X given some evidence E. And we will basically use a simple trick. We will just reject all the samples that do not match the evidence E. And you will see in an example now how this works. So let's say we want to estimate the probability that it's raining given that the sprinkler is on using 100 samples. So 27 samples have the value sprinkler is true. So out of these samples, for 8 of those, 8 rain is true and 19 have rain is false. So how would I now compute the estimated probability that it's raining given that sprinkler is true? Maybe you can just type it in the Zoom chat. You can just type the two numbers and a mathematical operation. I don't want to say too much. Yes, it's 8 over 27, exactly, because 27 is the total number of cases, and in 8 of these cases, we have rain is true. Correct. So this is then the solution. So obviously, you can also say we use normalization. For 8 samples, it's true, and for 19, it's false. So in overall, the probabilities should sum up to 1, and then you have the same result. So 8 over 27 equals 0.296, for instance. So let's say you have another case. Let me just take the pen. It would be, okay, you want to know the probability of rain given sprinkler is true, and for instance, that day equals Monday. And additionally, maybe you had cereal for breakfast. So breakfast equals cereal. And maybe you're wearing the t-shirt that you're wearing has a yellow color. Okay. Okay, this is a totally realistic example that everybody's interested in, of course. And the question is now, if you use rejection sampling, and also my writing wasn't that great, but it's because I don't have a great pad. Of course, it's not my handwriting. And so the question is, if you use rejection sampling, what issue might you have? And again, please type or even just talk. That's also fine. Yes, we will have to create a lot of samples because most of the samples would be rejected. Because we would have samples where the day is Tuesday. I had maybe bread for breakfast, or I just had a banana for breakfast, and maybe on many other days I don't wear a yellow T-shirt, but maybe I will wear a red T-shirt or blue T-shirt or whatever. And the more evidence you have, or the more conditions you have, the harder this becomes, right? Sometimes you then might need millions or billions of samples to just get 3 or 4 cases that make sense, or that you can actually use. Yeah, okay, thanks for the comment of Dan. I'll keep this in mind for next time. Okay. Oh, yeah, I have to close this first. Okay, so let's just discuss again rejection sampling a little bit more theoretically. So what are we doing? We want to compute this conditional probability here. And by the definition of the algorithm, so you have seen we use some normalization of the joint distribution of the actual of the event we're interested in and the evidence E. And then by using Monte Carlo simulation, we will obtain this by counting the number of cases where X and the evidence is true divided by the number of cases where the evidence is true. So to go back, the number of cases where the evidence is true was 27, and the number of cases where rain was true was 8. So here we would have 8, and here we would have 27. And if you use again the rule of big numbers, so that the probabilities will converge if the number of samples is big enough, which was shown here on this slide, then you can replace the numbers with the probabilities. And this, by definition, the joint distribution divided by PE equals then the conditional probability distribution. So what we see here again is if the number of samples goes to infinity, then the probability that we obtain from Monte Carlo simulation using rejection sampling equals the probability, the true conditional probability. Okay, so as we already discussed, this is hopelessly expensive if the probability of the evidence is small, and this drops exponentially with the number of evidence variables. So the more evidence variables you have, so in our case that I had we had 4 in total, then you can imagine that every additional evidence you have, the number of samples that you need in the end becomes exponentially higher. So it's some constant times the number of, to the power of the number of evidence variables. Okay, and to counteract that, people have invented likelihood weighing. So the trick is actually very simple. So you're just sampling non-evidence variables. So the evidence variables are not even sampled. In this way, you create just a few samples, and every sample that you create is useful, essentially. This is a special case of importance sampling. For those that are more familiar with these different techniques in Monte Carlo simulation. And the basic idea, as I mentioned, is you fix the values of the evidence variables and only sample non-evidence variables. And since not all events are equal, what we have to do then is we have to weigh each event with the likelihood of its occurrence. So because you cannot just ignore the evidence, of course, you then have to factor in the the outcome of the evidence in your overall computation by weighing the samples. So the easiest way again is to look at our sprinkler example. Now we want to know the probability of rain given that sprinkler is true and wet grass is true. So we already set sprinkler and wet grass to true. This is not sampled at all. And initially all the samples have the weight of 1. Again, we sample cloudy, and in this case it's true again. And because cloudy is true, we would have created sprinkler true with a probability of 10%. And because we're not sampling here, we are just changing the weight. So we take the previous weight, which was 1, and multiply it with 0.1 to get a new updated weight. Because we have to consider the fact that we already set sprinkler to true. Next, we go to rain. Rain is again a non-evidence variable. So here we will provide a sample again. And with 80% probability, this will be true, given that cloudy is true. And actually, we have rain is true. And now finally, wet grass would have been true, given that sprinkler and rain is true with probability of 99%. And again, this is factored in by changing the weight of our sample so that we multiply the previous weight with the new added weight, and then we have a new final weight. Okay, so the question now is, if we weigh these samples and then sum up over all the weighted samples, and do we get again a proper probability distribution? And of course, this is a rhetoric question. Otherwise, I wouldn't show this to you if this would be completely nonsense. And we will briefly discuss this. So we denote the non-evidence variables, including the query variable x by z. So that again, because we have a Bayesian network, we obtain the probability of the samples using the conditional probability of zi given the parents of zi. And then we additionally compute these weights. So if we have an evidence variable, we will not sample, but we will create this weight. And if you multiply all the weights, then you multiply basically also again these conditional probabilities given where you have the probability of the evidence given the parents of this evidence. So again, if you go back here, we computed the probability of sprinkler is true given the parents, which is cloudy. And here we computed the probability of wet grass given the parents sprinkler and rain. And these weights have been multiplied with each other. Okay, so now what we will do in the Monte Carlo approach is we will multiply the weights with the number of samples. And if you do that, we basically have these multiplications from 4 and these multiplications from 5. And these become in the end the joint probability distribution. Why? Because all the variables in zi and all the variables in EI, so all the evidence variables and all the non-evidence variables together form the set of all variables. And because we are multiplying here two products, this again becomes one big product. And by just renaming these variables, it's the same as computing the joint distribution using our previous formula. So because we can just rename the zi and the EI to new xi names, and here we have multiplications and here we have multiplications, and these two multiplications are multiplied, these formulas are identical. Okay, so this result 6 we will have to remember now to check the consistency of likelihood weighing. So the weighted sampling probability is then computed as follows. So p hat of x given e is then computed by normalizing the weighted number of samples using likelihood weighing technique. Now what we know is that when the numbers are large, we can replace the number of samples with the probability of creating these samples. And by using equation 6, we know that S times W equals the probability of Z and E. So Z contains X and Y, So here we have probability of x, y, and e. And because we're summing over all y's, which are the hidden variables, we just have the probability of x and e. And by the definition of this normalization rule, we also know that this is then again the conditional probability of x given e. And again, we see that when the number of n goes to infinity, the estimated conditional probability approaches the true conditional probability. And of course, the performance still degrades if you have many evidence variables, because only few samples have nearly all the total weight. But this is a more efficient approach compared to rejection sampling. All right, so to sum up, probabilities express the agent's inability to reach a definite decision regarding the truth of a sentence. So of course, we obtain more information compared to just checking whether a certain statement is true or false. Nevertheless, there are applications, of course, where you don't want to have any uncertainty left. For instance, if you look at safety critical systems, which is also like a research topic that we research a lot in my research group. So now I used 4 times research in the one sentence. But in other applications, of course, that are not safety critical and where you want to know what is the most likely outcome, then of course, this gives you much additional information, also because you can consider that certain facts or information in the knowledge base might not be correct. So if you would, let's say, create a knowledge base from Facebook, then I would certainly use probability distributions. If you create a knowledge base from Wikipedia, then maybe you can use logics. So just to don't take this too seriously, but it's just like a rough or like an intuitive explanation when you should use what. So Bayesian networks are then used to represent conditional independence. I mean, by using conditional independence, we can drastically reduce the number of probabilities that we have to store to do probabilistic inference. So with just very few number of probabilities, we can compute any other probability distribution that we're interested in without needing this exponentially growing table of joint probabilities that we would have if we would do it in a brute force way. And inference in Bayesian network essentially means to compute the distribution of query variables given a set of evidence variables. And as I already mentioned, this can be computationally expensive. So what we have additionally shown is that you can approximate these probabilities using Monte Carlo simulation. And there we used rejection sampling and likelihood weighing. And of course, Monte Carlo simulation provides a trade-off between accuracy and efficiency. So if you just want efficiency, you just use a few number of samples. If you want to have a lot of accuracy, you use a lot of samples. And at some point, it's even cheaper to compute the exact probability than computing using Monte Carlo simulation with 1 billion samples. That is kind of obvious, but yeah. So if you really want to be precise, then you should use Monte Carlo simulation, of course. And then it also becomes quite inefficient. Okay, so yeah, there was a question in the chat now. Is there any reading reference if somebody would like to expand on the concept of Bayesian networks? Yes, there is. Where was it? Here. I mean, I can also go back to the very beginning that we had all the references. Oh, actually, no, it's only as a footnote later on. Maybe we should place this more prominently in the future. This is the, wait a second. I'm almost there. Here. So this book from David Barber, Bayesian Reasoning and Machine Learning. I think this is a quite good book. As I said, it used to be online available and freely available, but when I checked this year, so it was now finally published. And somehow it was not so easy to get the latest version. I think now you have to buy it, but as I said, I mean, the older versions were all on the web available, and maybe we can put up an older version, but we would still check whether this would be legal or not to do. Okay. So is the book exam relevant? Oh no, I mean, the thing is, again, what is relevant for the exam is always aligned with the learning outcomes. And it's also like the exercises should be aligned with the learning outcomes, and there shouldn't be anything in the exam beyond this. Yeah, what is relevant for the exam is that you compute these probabilities of Bayesian networks. That's, for instance, something that occurs quite frequently in our exams, that you have something given like this, and we want to know what is the probability that John calls given that there's an earthquake and a burglary or something like that. Another thing that is where you should practice a bit is, if I ask you, is burglary conditionally independent of earthquake given John calls? This is also a rather typical exam question. Yeah, I mean, also like we had once an exam question about Monte Carlo simulation, but they are not occurring that often because these examples have to be quite small. Yeah. Okay, good. So then we stop a little bit earlier today with the lecture, because then we have more time for the exercise today. And then I would hand over to Adrian, and maybe there will be a 5-minute break, right?
Yes, I would suggest like we'll meet at 35 so that I have time to set everything up.
Okay. So as always, I wish you a nice weekend, and enjoy the season, the Christmas season, and see you next week then.
If you can start the recording. Perfect. Then hello everyone, and welcome back to this exercise session in Logic. Let me just make sure that I also see the chat. Okay, that's going to be a bit tricky. Now, again, if you have any questions, perhaps do it on Tweetback, because for me, the Zoom chat kind of disappears. So yeah, if I don't see your question there, then yeah, try it on Tweetback. Okay, so this exercise session is going to be mostly about first order logic. And the first thing that we will have to do is investigate for certain types of sentences whether or not they are actually first order logic sentences or not. And the thing that we need to look at first is, well, how do we actually construct a first order logic sentence? And so we have different types of elements that we can use. And the most basic ones are those ones. So basically just variables, which, yeah, it's always an interesting discussion. You have to imagine variables like placeholders. If that sounds natural to you, then all is fine. But some students are like, okay, but it's a letter. Is it something special? It's more of a placeholder. But yeah, perhaps I can answer that kind of question when they come. Then you also have connectives that we used in propositional logic as well. We then have the equality sign, which you theoretically can write in a different way. It's just like you can write it with quantifiers and that sort of thing, but it's definitely easier if you accept the fact that, okay, we use equality. It's a sign that you know and that we allow ourselves to use. And then we have quantifiers, which really change the game here, and they are the reason why first order logic is so much more powerful than propositional logic, but also why first order logic is typically much more complicated to solve than propositional logic. But we will see that in more detail later. So then we have also syntactic elements like constants. Those are just, I mean, certain types of objects which do not change. So for example, King John, which refers to the object King John, the number 2, which refers to the object, or rather the concept 2, right, or 2. Then we have predicates, which are basically things that associate a true or false value to a certain object. I'll come to that in a minute. And then we have functions which take objects and map them to other objects. And typically a question that we get at this stage of the lecture of the exercises is, okay, but like a predicate, it's nothing else than a function, right? Well, not for us, because so a predicate, what it's going to do, it's going to take some sort of object. So that can be a constant. Whoops, that's supposed to be an O, constant, variable, whatever. And it's going to send it to a true or false value. Okay. And on the other hand, we have functions which sort of do the same. Like they also take objects as an input, but they send it to other objects. Right. So, for example, I can have a function that, given a car, is going to give me a reference, if you will, to the right front wheel. Right. So that would be a function. And the predicate is really something that gives you only true or false. So if you are really picky, you can also say, yeah, but a predicate is nothing else than a function, but it gives us an output, a true or false statement. Right. So in theory, it's sort of the same. That is more or less true, but we're going to see a bit later why this difference is very important for us. So you should really keep in mind, okay, a predicate and a function are not the same thing for us. Okay, one deals with true or false, the other deals with objects, like gives us objects back. Okay, now that we have discussed this, I'm going to give you a good example afterwards, but I need to dive in the exercise a little bit later on. So let's leave that here for now, and let's look at how we construct first-order logic sentences. So the idea is that we have simple terms. So a term is nothing else than what I called before an object, right? So it can be a function of another term, it can be a constant or a variable. And then using those terms, we can create atomic sentences, which are just either single predicates, which may not have any arguments, or the predicates of a term, or a term equals to a term, right? Because this equality sign that you can see here is sort of like a predicate, right? Yeah, and then we can construct more complex sentences, which are going to be the first order logic sentences it's going to be what we understand as first order logic sentences, which are just sentences with brackets, with some sort of logical connector here, like in propositional logic, or something with a quantifier variable, and then some sentence on which it refers to. So I see a question, can functions have multiple inputs or arguments So inputs, yes, we're going to see it. You also have it in the lecture, like an n-ary function is a function that allows multiple inputs. And for the outputs, no, I think it was just for the outputs. For the outputs, I think it had a different name, but I cannot remember right now how it was defined in the lecture. I think we spent a bit of time on the difference between a function and that other term, but I can't remember. Whoops, what is that? Sorry, that is not on my side, that is another computer. Yeah, sorry, it stopped. There is like a central computer in this meeting room, and I have no idea who tried to call here. Anyway, isn't term equals term a predicate? Yes, pretty much, or at least it works like a predicate. That's true. Yes, so we're going to see an example of functions that actually have more than one input argument. Then, if I remember correctly, the iBook defined functions as relations in which there's exactly one output. Exactly. So you can have multiple inputs, but you have only one output. And predicates also can have multiple inputs, right? I mean, for example, the equality predicate, so to speak, is a predicate that takes two things as an input, but it always gives one output in the sense that it gives either true or false. Okay, so let's dive into the exercise, because I think a lot of stuff will become a little bit more clear when we look at live examples. So here we have a set of symbols, D, F, and G. D is a constant. F is a function symbol with two arguments. So you see here, it can have more than one input argument. G is a function with 3 arguments, and we have a bunch of variables, whatever. So let's look at the first one. So here we have G, which is a function with 3 input arguments, and we have it applied on D and D. So yeah, that's not quite correct, right? So that's wrong. And a correct one would, for example, be, oh dear, my writing is absolutely terrible today, my apologies, would be something like this. Okay, so that would be correct. Then let's look at the next one. We have here F, which is a function of 2 arguments applied on X. Okay, works. G of some stuff. Okay, works. D, now it doesn't work anymore because F was just a function of 2 arguments. So that's incorrect. Now let's look at this one. So we have G, function of 3 arguments applied on X. This thing, which we'll have to check later, and this thing. So 3 things. That works, no problem. Then we have to double check what happens inside here. So we have a function F of 2 elements. F was a function with 2 arguments, so that works, not a problem. I see a question, but we cannot check if GDD something is semantically equal with GDD, right? So I mean, if there was a variable, right? Oh, okay, so you mean that this would mean something like that, right? And here something happens and we don't know what happens. Well, that's not the case, because if we had meant that, we would have needed to put a variable here, right? But we didn't do that, therefore that's not the intended meaning here. It's just basically an error in this sentence that we wrote down here. So let's continue with the last one. So we have G, function of 3 input arguments. Let's check. 1, 2, 3. Okay, works. Now H, here we have a problem, because H is actually not defined. We only had D, F, and G. And you obviously have to define the things that you need before you actually use them. Otherwise you have an error. So that one is also incorrect. Okay, so that concludes that part of the exercise. Let's go to the next one, which is perhaps a little bit more interesting. So we have a constant m, a function symbol with 1 argument this time, and 2 predicates with 2 arguments. So let's check the first one. So here we have a predicate applied onto 2 things, right? So yeah, that works, no problem. Here we have again a predicate with 2 input arguments applied on 2 input arguments. Okay, works fine. Then we have f applied on something. Works also fine, because f was a function of 1 argument. So all good. And now it becomes interesting, because here we have a predicate with 2 arguments, right? So that works. We have 1 here and 1 here. However, we have here a predicate which, remember, is applied on objects, but this time it's applied on something which returns a truth value. And this cannot be, this is not okay. So this is wrong. To give you an example of why this cannot work, let me take another example where I have the predicate red, right, which checks whether a certain object is red or not, right? So this gives true if and only if X is red. Now, if I do something similar than in exercise 3 here, if I do, for example, red of X, right? Let's imagine that X is indeed red, then I would have true here. And so I would need to evaluate the redness of the concept of truth, right? And that just doesn't make sense. And so that's the reason why this thing is not allowed. We only allow in input arguments of predicates something which is an object, right? Okay. Yes. Then there's the question, why is f of m okay, but not b mx? So this part, like if you just take this thing, oops, then that's okay. That works. That's not a problem. But the thing is that we are plugging in the output of this predicate into another predicate, like I did here, right? And that's not allowed. That's not okay, because it's just wouldn't make any sense. Okay. I hope I have presented well the difference between like a truth value and an object, so to speak. But yeah, if you have any other questions, don't hesitate to ask further. We have plenty of time today. So the next one is, so again, a predicate applied onto two objects, not a problem, works fine. Then we have a logical connector. Okay, still all good. And then we have a quantifier with a variable. Okay, still allowed, not a problem. And a predicate applied onto two objects, and then the whole thing with parentheses. Those are all things which are perfectly fine, and therefore we can allow it. So I see a few other questions, so let me just finish this exercise and then I will answer them all at once. So here you have a predicate applied onto two objects. Again, that's what a predicate is supposed to do, so all good. We have a logical connector again, still all good. We have a predicate applied onto this thing and this thing. So for now, all works fine. We just need to check this thing. So we have a function applied on, again, an object. Our function f was with one input argument, so all good so far. And then f applied on x, again, still all good because it's a function applied on one thing. So that is fine. Okay. So let me answer the many questions now. So predicates cannot be another predicate's argument. Yes, that's correct, because the input of a predicate is an object and it's not a true or false value, because otherwise, yeah. I mean, that's basically how we define things so that it makes sense for us naturally. Is the output of the predicate a term? No. A term is, so a term was the same thing that what I called at the beginning an object, right? I just used the word object because it was perhaps a little bit easier to memorize what it is, but the correct thing is to call this is term. So no, the output of a predicate is not a term, it's a true or false value. What if m is a Boolean value? Well, that's the thing, right? So we define constants as not being Boolean values, okay? So yeah, that's how we need to separate sort of the things defined, because otherwise it becomes a mess and we can't work with it. I don't understand this. Why is f of fx okay, but b of bm not? So again, so b of bm, I mean, assuming it's a predicate with one argument, right? It's the same as here, right? It's basically exactly the same. I cannot check if the concept of truth is read or not, right? It just does not apply on this thing. So yeah, those are two things that I cannot apply it towards. But if, for example, if I have, for example, a function f here instead that gives me the right wheel of a certain vehicle, then I can check if, okay, if m here is my certain vehicle, then I can check if that wheel is actually read or not, right? So in that case, it works. Let me take that away again. Okay, but father John is okay. That depends how you define father. Like if father is just something that checks whether or not he is a father, then no, because it would be a predicate. But if it gives you, if it returns you the father of the object that you feed it, then yes, that was a very strange sentence. But yes, anyway, then it would be a function and then everything would work. but can't a predicate accept a Boolean as one of its arguments? No, that's how we define our logic, right? That's how we define our entire system. You can perhaps change the definition if you really want to, but then everything becomes a mess, and then you have stuff like this right here that is allowed to happen, and then it just becomes very difficult to compute with. So that's why we separate those two concepts. Okay, so then we can continue with the next exercise, I guess, where we are going to see what is sort of how we have to handle universal and existential quantifiers differently. So here we have two types of people. We have those that take the bus and those that have a ticket for the bus. And everyone is well behaved in this case because everyone that does take the bus does have a ticket. And so if we look at the sentence, all people who take the bus have a ticket. Well, who takes the bus here? It's just Alice, and she does have a ticket. So in that case, this sentence is true. Okay, and this is going to be important for us. But let me just say here, so we are restricting ourselves to the case where there are only 3 people in the universe. And one more thing, so perhaps I'm going to blow the mind of some people, I don't know. But it took me actually, I only realized this in my last year of my master's, that actually when in exercises you have Alice, Bob, and Charlie, it's because you then have A, B, C. Anyway, for me, that blew my mind at the time because I didn't realize it sooner, but yeah, anyway. So the sentence that we have here is true in that context. So what we want to do now is that we want to check if this formula correctly sort of formalizes the sentence that we had here, right? We just want to check if it works or not. And one way that you can do this is, especially if you only have a limited amount of things or participants in your universe, so to speak, you can actually transform this sentence into propositional logic so that it's a little bit easier to handle. So for example, if this sentence, so if this thing here has to hold for all x, for all persons, then you can just write it equivalently as, so it has to hold for Alice, right? Oops, this might take a while. And it has to hold for Bob. And it has to hold for Charlie. Okay, so it has to satisfy all those things for all the people, so to speak. And now it's a little bit easier to check if that sentence is actually true or false, right? Because I can just plug in what I had on this side. Yes, it's here for me. So here in that case, that would be true, true, false, true, false, and false. And you can see here that at least one of the elements here is false. And so this entire thing is false. And that's a problem because on the page before, we said that this thing is true. So the sentence above, it's not a correct formalization. Instead, what you should use in that case is for all x, bx implies tx. So that would be the correction. Now you can check this by yourselves that this does actually work in that case. And this is sort of the moral of this exercise, right? If you see a universal quantifier, you should think about an implication and not an and. Okay, this was also discussed a little bit in the lecture, but you can sort of see here that universal quantifier sort of automatically goes with an implication. Okay, let me check a few questions before I move forward. Does exist S, Z, Y? So I guess you mean this thing here, right? Mean there exists Z and that are satisfied meanwhile. I'm not sure what you mean here. So this part would just mean there exists a Z such that S of ZY is true, right? Yeah, perhaps you can make it a little bit more precise. Could you please show the solution for problem 521? Like this entire thing? No, sorry, because then I'll definitely not have enough time today. But you can just watch the video again. Yeah, I think I did it rather detailed. Yeah. So let's move forward to the next one. I mean, I can perhaps see at the very end of the exercise if I still have a lot of time. But yeah, let's move forward for now, and then perhaps I'll go back. Okay, so this time we have actually a different table, right? And here nobody actually takes the bus, and we are looking at the sentence. Some people who take the bus have a ticket. And I know for a fact that this sentence confuses a lot of students. And so the actual meaning behind it is there's at least one person that takes the bus who has a ticket, right? And so in that case, nobody takes the bus, right? So we cannot even check if they have a ticket or something like this. So in that specific case, the sentence is false. Right? Because there is nobody, there is not a person that takes the bus. And the thing with the ticket doesn't matter in that case. Okay. And if you think, okay, yeah, this is strange because that sentence is asked in a very strange way. Well, the funny thing is that in the next exercise, you have exactly the same thing, and there it's going to make sense for you. So yeah, it's just, I'm still not quite sure what psychological effect is happening here. But yeah, for some reason, even for me, this sentence is a little bit confusing. Anyway, so this time we are going to look at this formalization, and we're going to check if it is what this sentence means. So how do we transform this into propositional logic this time? Well, again, since we have a limited number of participants, we can rewrite this. If it has to work for at least one X, right? It means that it has to work for Alice, or that it has to work for Bob, or that it has to work for Charlie. Yeah, so at least one of those possibilities. Now, we can do exactly the same as we did before, namely just put the values of each variable that we, or propositional sentence that we have here. So here we actually had false, 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 and then it doesn't quite matter, but let me just write it. And since whenever you have an implication and the left side is false, then the implication itself is always going to be true. So this thing is true, this thing is also true, and this thing is also true. Therefore, this means that this entire sentence here evaluates to true. Now I see some questions. Let me just finish this and then, yeah. Okay, so this evaluates to true, except that we had at the beginning that this sentence evaluates to false, right? So that's that doesn't work. So it's not a correct formalization. And the correct one, actually, perhaps some of you might already have guessed it, is this time the other way around. It's this with an and. Oops, I forgot to write correction again. Okay, and so this is, again, the moral of the story here. because when you see an existential quantifier, you should automatically think, okay, there's very likely going to be an and here. Like sometimes it can happen that it has to be an implication, but typically when you try to formalize a sentence and you see, okay, there's going to be an existential quantifier, then 99% of the time it's going to be an and, right? Or an or something like this, but not an implication, right? This is also discussed in the lecture. Actually, I can't quite remember exactly the slides, but it's something about, I think, smart people at TUM, something like this. And there it's actually shown why if you put an implication here, even in natural language, it wouldn't make sense, okay? So yeah. Keep that in mind. If you have an existential quantifier, then you most likely have an and if you have a universal one, then you most likely have an implication. Okay, question time. I'm not sure which one you mean with 521. What did you mean 5? Oh, 521. Sorry. Then I misunderstood. I thought you meant this one. Okay, here I can definitely explain it again. So here in that case, I just need to check if that sentence here is true, right? So here all I need to check is that all people who do take the bus do have a ticket, right? So who takes the bus? Well, it's only Alice. Does she have a ticket? Yes or no? Well, yes, she does. Therefore, this sentence is true, right? When will the other grades bonus exercises be released since the common road goes? So the programming exercise for logic is actually coming next week, that I can tell you, but it's going to have a little bit more time for you to solve because Christmas and so on. Who the F is Alice? Yeah, it's actually you have mathematically correct way of naming your characters. It's a whole Wikipedia article. So you have Alice, Bob, Charlie, and then I think it's Dan. I'm using it in the exercise afterwards as well, and then I can't remember. Anyway, can you explain why your whole sentence evaluates to true when the left side is wrong? That's just how implication works. That's how we defined implications, right? Because you have this. Do I have space somewhere? Yeah, here perhaps. You have this truth table, right? That if you have true, 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 false, false, true, false, false. Oh, I think I just did a mistake because now I have to remember the truth table of the implication. Dear. Okay, so this is true, this is false, this is true, and this is true, I think. Yes, I think that's the one. So that's just how we define implication, right? Why we use the all quantifier for some people, or there exists at least one. The all quantifier, I think we only use it here for all people. Like here it's clear why we use it in that case, because it's all people, right? I think, yeah, okay, then that might be for later. I already know where you're coming from. We'll see. So what's the difference between 524 and 523? 4. It's the same sentence. In that case, it's the same sentence. I'm just taking the thing that I have here to motivate what I'm doing afterwards. Where can I find more example about universal quantifier with implication? Oh, we're going to have a lot of them, namely from here on. So let's continue with this exercise now. Don't worry, you will have plenty of sentences like this. So here we actually are trying our first steps in how to formalize certain sentences, right? So I have here predicates that checks whether a person X admires a person Y, a predicate that checks if X is a professor, and a certain constant Dan. And one thing that I forgot to tell before, this is going to be like this and this and this thing is going to be the exercise where you're going to hate me. And you're going to hate me for a very good reason, because whatever sentence I'm going to write here, there's certainly one person that might think, okay, but actually I would have written this differently. Is perhaps this other sentence also correct? Because the thing is, in first order logic, you have a lot of equivalences between different ways of writing. So for example, this thing, nobody is a professor, would actually be the same as saying there does not exist someone that is a professor, right? So those two sentences are perfectly equivalent. And so I would just ask for your patience here, because I think we are already quite, we don't have that much time anymore. But if you're wondering, okay, but I'm thinking about a completely different order sentence, then perhaps the best thing to do for you is to look in the solutions that I have already posted. They are already online on Moodle. And if you don't see your solution there, the next thing, definitely go ahead and ask it here in the tweet back. But if you see that I'm struggling and that I'm taking a little bit too much time to answer your question, please don't get frustrated and do ask your question on Moodle, because they'll just have much more time to answer it properly and to show you the difference between what is the correct sentence and why yours is good or might be wrong. So yeah, as I said, please don't be frustrated and ask your question on Moodle if I don't have time to do it here. Just one thing though, if you want to check if two sentences are the same, you can transform, let me write it much faster. You can transform it to CNF. Actually, I can take away the one. You can transform it to CNF and then compare, because the CNF, the conjunctive normal form, is unique, of course, up to reorder. So if you order the clauses a little bit differently, then of course it's not going to be the same sentence. But if, as a general rule, if you want to check if a certain sentence is the same as the one that you had in mind, transform everything to conjunctive normal form and then check the differences. Okay, so those two warnings being said, let me continue with the exercise, and namely with this one. So Dan admires every professor. So here you have an every, so you should immediately think, okay, there's going to be a universal quantifier, okay? And so this universal quantifier will have to be applied on every professor, okay? So I'll certainly have to check if somebody is a professor. And you have Dan admires then that person. So admires DX. And here's where the rule of thumb from before is going to be useful, because we have a universal quantifier here. So it's basically going to be an implication, but it's either in that sense or in that sense. So let's just check which one is the wrong one. Yes, so it's that one. So if that one would be correct. So if we had used this implication here, it would mean, so for everyone that Dan admires. So if Dan admires that person, then it implies that that person is a professor, which is not quite the thing that we had in mind here, right? It's the other way around. If that person is a professor, then Dan admires that person. So the implication has to be in that direction, okay? Now let's continue. Some professor admires Dan. So here we have to think, okay, some, okay, then it means there exists, right? There exists some professor, so this is going to be my professor. And that person then admires Dan. So admires, that person admires Dan, okay? And again, the rule of thumb says that if we have an existential quantifier, then we probably want to use an and here. And that's indeed the case, and that's then the correct sentence here, okay? Now the last sentence is Dan admires himself. This we just did because, yeah, it was a funny sentence. So let's just write it like this. It's pretty easy. Okay, let's go to the next sub-exercise, because this one is a little bit harder. Let me just answer a question that I just saw. What is the difference between ADX and AXD? So ADX means that Dan admires that person, and here it means that that person admires Dan, right? So yeah, that's just it. So here we have now a predicate that says that X attended a lecture. Oh, wait, there is an error. You say 5311. No, it is correct. Dan admires every professor. Everybody that is a professor is admired by Dan. Yeah, no, that's fine. That's, yeah. Okay, more questions. Let me answer those first. I can exchange X and Y in all examples, right? They are just variable names. Yeah, it's even more general than that. That's why I said you shouldn't focus on the sign that you use for the variables. It's just placeholders, and it's just there. Like the difference X and Y is just to make sure that yeah, we don't confuse them. Yeah. For the third one, for the third one, this one, okay. No, I think that's something else because there's no professor. There's no professor involved here. So again, explain Dan admires every professor again, please. Dan admires every professor. So everybody, basically, we need the predicates. Somebody is a professor, and Dan admires a certain person, which happens to be the professor, right? And so yeah, we just need an implication, and this implication just has the meaning here that if I have a professor, then Dan is going to admire that person. So one is not correct. I think it should be for X is not a professor. Aha, but here you see, ha ha ha. That's exactly what I meant. So somebody said for all X, if I do not have a professor, either I have not a professor or Dan admires that person, but that is nothing else than just an implication removal, right? So this is literally just the same. Actually, I should do a logical equivalence here than this thing. It's exactly the same sentence, right? And that's why I said transform everything to conjunctive normal form, and then you will be able to see. But I am afraid we really need to move a little bit forward. So let me check if there are some questions that are true. So for the third one, well, we always assume that this thing is true that we give, right? So that's, yeah. And again, yeah, anyway. Shouldn't Dan admires every professor be the entire same thing as every professor is admired by Dan for 5311? Yes, I mean, you can, that's exactly what it means as well. Like everybody that is a professor is admired by Dan. The second one, if the right part, px right arrow xd, no. So if you use here an arrow, if you use here an implication, it would mean, I mean, it could also be that nobody is a professor, right? If you allow this to happen, it could be that absolutely nobody is a professor, and then that entire thing would be true, right? And so that's not what we want. Okay, but now I'm afraid I need to go a little bit faster through the other ones. Yeah, so we have the predicate X attended Y. We have the predicate if it's a student, if it's a lecture, and we have no student attended every lecture. And the way I like to think about the sentence is a little bit different than how it's written here, but again, you can check in the solutions how exactly to reformulate it. I like to think that for every student, there's at least one lecture that that person does not attend, okay? So what I just said was that for every student, so this is going to be my student, there is at least one lecture, this is a lecture, and that it did not attend, right? And so now I do it sort of chronologically, so to say, right? So I had first the student, so I need to check if it's a student, and then I had the lecture, so I need to check if it's a lecture. And here I can use, again, the same heuristic as before. So here I just need to put some brackets because it's one and then the other, right? And the heuristic tells me that, okay, I have a universal quantifier, so I need an implication here. And here I have an and, so an existential quantifier, and that's why I need an and. And that's sort of how heuristically I can construct this sentence, okay? Now, again, you might have completely different ways on how to come on to that sort of sentences. That's all fine. But this is perhaps the easiest for me to explain using the heuristics that we found before. Now, again, if you look through the solutions, there are plenty of other formulations for this. So let's go to the next one, which is going to be no lecture was attended by every student. So in other words, for every lecture, there is at least one student that didn't attend it. So this time I have to write for every lecture. This is going to be this time my lecture. There is at least one student that did not attend it. So not attend. Now I need to swap it because this time Y is my student. And now I do exactly the same as I had before, right? So I need to check if it's a lecture and I need to check if it's a student. I put the brackets because it's one after the other. And again, same heuristic, an implication, an and tada, that's my sentence. Let me do the last one and then I'll check the questions. No lecture was attended by any student. So here it's a little bit different because basically for every lecture, for every student, it was not attended, so to speak. So this time I have a double universal quantifier, right? So this is going to be my student, let's say, and this is going to be my lecture. And so I want to say that students did not attend it. Like no matter what, nobody attended any lecture, right? And so here it's a little bit more tricky. You can actually, I think as far as I know, you can write it. I wrote it a little bit differently in my notes. So you have to check if it's a student. You have to check if it's a lecture. And basically you can then write it like this. Again, using the same heuristics that we had before. It might be written a little bit differently in the solution, but that's basically how you can do this. Okay, let me go through the questions. I hoped we would have enough time for the last exercise, but let's see how far we come. Is it also fine to build the quantifiers in the sentence, or have they always to be written at the beginning? Yes, always at the beginning, because otherwise it's going to be extremely messy. Is there always only one correct formalization of a sentence? There is only one correct conjunctive normal form, right? Because as I said before, if you have something like this is exactly the same as this. So there's not only one correct formalization, but if you transform everything to conjunctive normal form, which would actually be this thing, then it's completely unique, okay? When to use implication and when and, well, that's what I said before in the other exercises. When you have a universal quantifier, you want to use an implication, and when you have an existential quantifier, you want to use an and. Whoops, that was too far. Okay, is it also correct is it also correct when we put S and X together, like S and X? Yes, I know what you mean. This is also how I wrote it into my notes. That would, sorry, it would be the other way around. That would also be correct. And again, you can see that by checking the conjunctive normal form. I do not understand when SX comes first and when LX comes first. Well, basically, it depends on how you started with the quantifiers, right? So here I said, okay, here my X refers to the student. So I'm checking first if it's a student and then the rest, okay? Here, first, my X in my sentence was the lecture, and therefore I put lecture first, and so on. That's sort of the idea behind it. Okay. Let's see if we can deal with the next exercise in the last 10 minutes, because not all of them are important. So I'm going to skip, I think, two. Two of them are like literally the same sentences. Actually, let me check. I think it's, yes, it's 2 and 3. Those are exactly the same. And XH. Yeah, let's see. Okay, so I'm going to skip 3, I guess, and the rest I'm going to leave as is. Okay, let me answer some more questions. How about which operator to use when we have not in front of the existential or universal quantifiers? Is it the same? Yes, basically you can use the same ideas behind it. When do we put brackets? Whenever necessary, because here you can see, okay, it's first I have to deal, for example, here, right? First I need to deal with the students, and then I need to deal with the lecture. And so I first deal with the student bracket, and then I deal with the lecture, and so on. I'm going to, for the bonus programming exercise, could we show on time how to edit an exercise? Not sure what you mean, but programming exercise I'll answer afterwards. But for me, it would sound much more obvious written like this. Yeah, that may be. Yeah, it's everything is allowed as long as it's the same sentence, right? So perhaps you can post your sentence to Moodle, and then I can check if it's indeed the same sentence. Yeah, that's a thing. It depends how natural it is, what makes more sense for you. If it's indeed the same sentence, then you might have a correct, let's say, logical understanding on how to formalize sentences. But yeah, I just chose this one because this one is easiest to explain, but you might have a completely different way of thinking, and that's fine as well. I mean, as long as it's the same sentence. But okay, let's go. So the quantifier applies to the whole sentence. That depends. If they are in the front of everything, then yes. If not, if they are like in a bracket or something like this, then they only apply to the brackets. So many questions. I didn't quite expect that. So we don't resolve quantifiers from inner to outer quantifiers. Yeah, that's it. We start with the inner ones and then we go to the outer ones, so to speak. I'm not sure if that answers your question, but yeah. Okay, let me start with this exercise, and if you have other questions, then perhaps I can answer them. Yeah, at the end of the hour or something like this. So we have here a predicate that tells us if X can trap Y, and we have Sherlock Holmes, and we have Moriarty. So, and now we want to say Holmes can trap anyone who can trap Moriarty. So here we already have an anyone, so we might already think, okay, it's going to be for anyone, right? So Holmes can trap anyone, so Holmes can trap that anyone. And then who can trap Moriarty? So it's applied on that anyone, so anyone trap Moriarty. So now we already know, okay, there's going to be a universal quantifier, so it's either an implication in that direction or in that direction. So what would it mean if we use this implication? It would mean that if Holmes can trap that person, then that person can trap Moriarty. Is that what the sentence tells us? Holmes can trap a person if that person can trap Moriarty. So it's not quite the same. So that is incorrect. And it's that implication that is the correct one, right? So now we do 2. Holmes can trap anyone whom Moriarty can trap. So again, we have a anyone. So for all X, Holmes can trap that person. So again, Holmes traps that person, and that person can be trapped by Moriarty. So it's MX. Okay, so again, universal quantifier. So it's either in that direction or in that direction that the implication goes. Let us try. I wrote it again the other way around as in my notes. So it is, okay, let's try this one. So this one would mean if Holmes can trap that person, then Moriarty can trap that person. Is it the same as what we had above? Holmes can trap anyone whom Moriarty can trap. That's not quite the same again, because we are interested, basically it's just Holmes that can trap anyone if Moriarty can trap that person as well. So that one is incorrect, and we have to go there. It might be a little bit confusing. I definitely get that, but yeah, just go through the sentences a few times. Yeah, it just takes a little bit of practice dealing with that sort of formulations. So this thing is, as I said, exactly the same as in the in number 2. So I'm just going to write it down but not explain it, because the idea is really exactly the same. It's just a formalization above which is a little bit different. And I think the other sentences are much more interesting, as a matter of fact. Okay, so if anyone can trap Moriarty, so I said it before, if you have an if, then you probably have an implication here. So if anyone can trap Moriarty, so here it's a little bit tricky because anyone can trap Moriarty in the sense that if there exists a person that can trap Moriarty, okay, so if there exists a person that can trap Moriarty, and then Holmes can trap Moriarty. So that's easy now, can trap Moriarty. And here you have to put brackets to make sure that, yeah, everything is well defined. There's a question about number 2, which was in the one direction. Yes, that's correct, but you also have to swap then those two things, and then it becomes literally the same as in 3, right? Because here I have Holmes on the right side, and here I had it on the left side. So it's exactly the same sentence, as a matter of fact. Okay. So here you are using existential quantifier with implication. Not quite, and that's why it's a little bit tricky here. Because here I'm only using the existential quantifier with whatever is inside the brackets, right? Because I mean, this X does not apply here. Right, and this is perhaps answers the other question. Can you explain the meaning of the brackets? This is just to restrict the validity of the existential quantifier to this thing and not this thing as well, right, on the right. So, yeah, I would actually like to finish this exercise today. So let me go a little bit above the time limit. Or do I wait for next time? Okay, let's see. Okay, let's see how far we come. So if everyone can trap Moriarty, then Holmes can. So again, we have an if. And so if everyone can trap Moriarty, so if everyone can trap Moriarty, and then we have then Holmes can. So Holmes can trap Moriarty. And here we see again that X does not apply on this part on the right. So there's a good chance that we actually need brackets, right? Because as a matter of fact, if we forget the brackets and if we had put the brackets like this, it would be a completely different sentence. I think, is that correct? No, that might not be correct. Yeah, it is. Yeah, it's correct in that case. So you should definitely put the brackets where they are here. Oops. Okay. Then let's go to the next one. What's that? Okay. Yeah, my apologies. Anyone who can trap. Can we do it still? Okay, I'll try to do it quick, and then I'll answer as many questions as possible. Anyone who can trap Holmes can trap Moriarty. Anyone who can trap Holmes can trap Moriarty. So anyone that can trap Holmes, right? And then we have that person can also trap Moriarty. And here it's again the same. You also need to use an implication here, and I'm going to do this quick. It's in that sense because, yeah, if that person can trap Holmes, then that person can trap Moriarty. Okay. Yeah. Okay. Perhaps. The other ones are very interesting, but yeah, perhaps I'll deal with them next time. Okay, and I'll answer just a lot of questions here. So are the brackets necessary because there is no X on the right side anyway? Yes, they are necessary because let me show you more or less how to transform it, how this would change the thing if you didn't use the brackets. So this is actually equivalent to if you use an implication removal to this thing. Right? This is just an implication removal. Then you use the De Morgan rule, and you have to reverse the quantifier x not txm or thm. And this is then, I'm putting the implication again. So this would be for all x, txm implies THM with the brackets here, so to speak. And here you can see, obviously, this is not the same as there exists an X like this. So the brackets here do have their importance. Oops. Okay. For all TXM, also okay for 4. Yes, but I think I've just demonstrated it here, but you have to remove the brackets then completely. Why do I need brackets? There's no X on the other side anyway. Yes, it depends. If you have an implication here, it does make a difference. Sorry, there was a typo from before. For the third one from 531. 531. 531. And the third one. For the third one, I mean, yeah, okay. That's a bit overkill. Your formula is a little bit overkill, but yeah, why not? Okay, yeah. Can you give an example of what it will mean if the brackets are put differently? Well, I think I've just done it here actually, right? Because here I'm putting the brackets like this, right? And here I'm putting them just like this. And it has a different meaning in that case. Is there a difference between the square brackets and the curly bracket and the other brackets? No, it's just, I don't know. I already used those brackets here. So I just wanted to emphasize the difference. That's why I used square brackets and not round ones. Okay. Yeah, how much do we still have to do? Those 3 ones. I don't know. Do you mind if I take 5 more minutes? Perhaps you can just write me either in the Zoom chat or on Tweetback if you mind that I use 5 more minutes. It's okay. Okay, good. Because those last ones are actually the most interesting ones in my opinion. So no one can trap Holmes unless he can trap Moriarty. This one is nice. This one is nice because there I need to use a different kind of thinking. So no one can trap Holmes unless he can trap Moriarty. So the way I like to think about this is that there does not exist a person. Okay. There does not exist a person who can trap Moriarty, who can trap Holmes, sorry. And then there's the unless he can trap Moriarty. Okay. So I sort of need to make this thing true if there does not exist, if there does not exist this person, right? So this unless, let me, oops. Yes, this unless, I'm going to write it and then I'm going to explain it. I want to write it like this, right? Because it basically means that if there's a person that can do this, and I know because of this negation that this has to be false, right? So whatever comes right after there has to be false. So if there exists a person, then either he, how shall I say, he should not be able to trap Holmes, right? So this should be false. And so the entire thing is going to be false, right? Or he should not be able to trap Moriarty, right? So it's either the one or the other one that has to fail, okay? Because I put this thing here, I'm not interested about what the person can do. I'm interested about what that person has to fail. And so it has to either fail to be able to trap Holmes, or it has to fail to not be able to trap Moriarty. Okay. I realized this sentence is a little bit more complicated. That's why I really wanted to deal with it. Again, there are other ways to write it. You can also put the negation inside and everything. But yeah, in 5337, he stands for one or Holmes. Good question. Good question. So this he stands for the X for the one, for the, yeah, not for Holmes. Yeah. Okay, then the next 2 ones, we are almost done. Everyone can trap. Okay, so everyone. let's think, okay, it's going to be an for all, can trap someone. So there is a someone, right? So everyone can trap someone. So everyone can trap that someone. Did I do it in the right direction? Yes. And then that person, someone here, who cannot trap Moriarty. So who cannot trap Moriarty. Yes. And so what connector do we use here? So you can actually see that the only variable here that is common to those two things is the y. And the y has an existential quantifier. So there's a good chance that we have to use an and here. And that's indeed the case. That's the correct sentence. So that's a little bit how you can solve that sort of thing with this heuristic, which I find very nice, because you don't have to think too much about, yeah, what's exactly the right logical meaning and so on. You can really make it very quickly with the heuristic. It might not always be correct, but yeah. Don't we need brackets because of the x? Yeah, but this time, I mean, where do you want to put the brackets, right? I mean, doesn't matter where you put them. If you put them here, then it's still the same. If you put them here, it's still the same. Here, it doesn't matter in that case, right? It just matters because of the implication, because it sort of changes the game a little bit. But yeah, you can test it yourself. If you put the brackets on certain places, then it's still going to be the same sentence. Okay, let me do the very last one, and then I'll do the questions again. So anyone, so I have an anyone who can trap Holmes, okay, whoops, who can trap Holmes, can trap anyone. So again, I have a y, right? And I have okay. This one is a little bit more tricky. So I'll write it here. Can trap anyone whom Holmes can trap. So Holmes can trap that anyone. Okay. So here the thing is, X can trap Y if Holmes can trap Y. So here you have the implication in that direction, and you have the brackets here. And anyone who can trap blah, blah, blah means that here you have the implication. And you can sort of see here the idea behind the brackets here, because here I sort of have to put the brackets here, because whatever happens after that, okay, it depends a little bit on X, but like internally, if you see what I mean. So yeah, it's this sentence is a little bit more complicated. So here you do have to think about the brackets a little bit, and if you put them in another direction, then you have to think about the intended meaning. So yeah, that takes a little bit more time. But yeah, okay, let me go through the questions. How complicated questions regarding logic can we expect in the exam? Will there be any very special cases? I would say in the exam, so the Holmes and Sherlock is, Holmes and Moriarty is a little bit too complicated for the exam. I would say something of this sort is typical for the exam, more or less, right? In 5337, 7. Oh yeah, I already answered that question. Okay. Doesn't we need brackets because of the X? I already also answered that question. Do we always need to put brackets if we want to quantify a variable which only appears on one side? Depends. It depends. Typically, yes. But as I said, for example, in this case, you can actually, like if you have written the sentence like this, it would be correct as well, right? So yeah, it depends a little bit how you come to that sentence. If you did it with the same logic as I had here in this exercise session, then it's certainly a good idea to always do it like this, because it's probably going to have the intended meaning. Typically how you do it, or at least how I do it, is when I see that sort of sentence that I have to formalize, I try it once with that heuristic that I showed you. And then once I have my finished sentence, I then check if it actually has the meaning that I wanted to give it. right? So it's sort of a two-step process. First you try, then you see if you failed, and if you failed, you correct a little bit the sentence such that it does exactly what you want it to do. What's the use of learning the logic stuff to the real research? So there's so many things. Let's do one which is a bit more technical. So there's something which is called temporal logic. For example, for cars, for autonomous cars, you want to formalize the traffic routes, right? So for example, you want to say, if I have a car in front of me and it goes goes with a certain speed, then I want to decelerate if the speed is smaller than a certain threshold, that sort of thing. And for that, you actually need temporal logic, which is just a slight modification of first order logic, right? So there you actually have literally traffic rules that you quite literally have to formalize, and this is not an easy task to do. We have some people at the chair who do that, if that interests you. I think I posted it in some of the forums. Sebastian Meyerhofer is doing that at our chair. Why can't we use an implication in 5338? Why can we not use an implication? Because try to use an implication and see where it leads you. Let's put it like this, because you're going to see that it doesn't quite have the same meaning. Like, for example, if I had an implication here, so what would be the meaning? Then I would allow that yes, I could allow the case that nobody is trapping no one. Okay, no one is able to trap anyone. Then that entire sentence would still be true. However, in this thing that I have above here, I'm assuming that for everyone, I can find at least one person that can that person can trap. Okay, whereas if here I assume that this is always false, right? Then this entire sentence would be true. But if I assume here that nobody can trap at least one person, then that entire sentence would be false, right? So that's why they would have different meanings in that case. Yeah. Okay. I think I've answered any question on TweetBack, at least on Zoom. I do not know. Oh dear, there's a lot on Zoom. I'm sorry, I really couldn't see anything on Zoom. Yeah, I'll just abandon Zoom and just see if there are any other TweetBack questions. Sorry, yeah, Zoom is always a little bit complicated for me. Is it correct to write TXH, THY, and yes, that is probably correct. Yes, I can imagine that this is correct. Will there be no exercises next week because there's no new exercise on Moodle? There will be an exercise next week. I just need to upload the next exercise sheet. It's going to be on Inference in first order logic. Okay. Yeah. I hope this answers all questions. At least on TweetBack, I don't see any more. Yeah, sorry again that I took 15 more minutes, but I thought the last sub exercises here were really the most interesting ones, and I didn't want to leave you without presenting them. So yeah, I hope you can forgive me. Yeah, next week 15 minutes shorter. That could actually be. I think the next exercise sheet is a little bit shorter. So yeah, let's see. Okay, then. Thank you, everybody, for listening, and I wish you a nice weekend. And Dawi, I think you can stop the recording now.